Welcome to TGIS 311, Maps in TGIS. This is day 5. I wanted to read you this quote. Every map deforms the Earth. It is impossible to represent a curved surface, the Earth, on a flat one, a map, without stretching, skewing, or tearing it. Map projections apply this distortion in a systemic way that allows you to control where and how it happens. You will not find a projection that is suitable for all maps. All projections distort the Earth in some way. Each one seeks to preserve some geometric property at the expense of others. And that is why we need to select the proper coordinate system and apply these changes to the coordinate system meticulously. And that's what this week is all about. In Lab 3, you will go through these steps for plenty of pieces of data and learn about how to select and apply these changes. As the course progresses, these labs will consist of new material being presented based on the foundation of skills you have completed in previous labs. The old material will be presented with little guidance in how to specifically accomplish them. Use of the resources presented in earlier labs, your notes, and the technical video resources. The goal is for you to build on your skills with decreasing reliance on previous labs for successful completion. As you proceed through GIS courses at UW Tacoma, you will be presented with tasks covering previous lab and classwork with little guidance. And that is how you will learn GIS. You'll perhaps need to look it up, and then you'll go back and apply it to the current lab. After a few times of doing so, the important aspects will stick and you'll be able to progress more smoothly as you get towards the end of the course. For day 5, 2024, the agenda is this lecture. It will be online. We're going to talk about spheroids, coordinate systems, defining coordinate systems, projections, and projecting. In class, the live portion, or Zoom, depending on what we do for your particular section, there will be lectures and demos. Particularly, we'll go over Lab 1 and 2 bonus maps and discuss them a little bit. We'll have some maps of the day if there are any submissions. And I'll have a series of Lab 3 important skills demonstrations to prepare you for Lab 3. And then, of course, you'll work on and complete Lab 3. This image, the reference will be provided. I have it here in front of me. It's oceanservice.noaa.gov. This is latitude and longitude, but the only ones labeled are latitude. And latitudes, as you can see, they go around the Earth rather than to the poles. So it's a continuous line that goes around the Earth. And you can see how the degrees are calculated from the center of the Earth and up to 90 in north. And then, of course, every 10 degrees, it drops down to 0 at the equator. In this slide, there's latitude and longitude again. However, in this case, the longitude is labeled. And as you can see in the image on the right, it's 180 degrees going around the globe. Going from north to south, either direction, and you can, depending on which hemisphere you're in. On the right, it's going from the northern hemisphere down to the southern hemisphere, but the southern hemisphere is hidden because at the widest point, you can't see below it. So these are the lines of longitude ranging from 0 to 180 degrees, going from north to south. And they're based on the Greenwich line or the international date line. That was where 0 exists. Critique this map on your own, and we will discuss in class. Particularly, I've added a couple questions to the left. What perhaps should be added to this map? What is clear? What is the emphasis? What care went into the labels or the symbology? What isn't clear? And what story do you think is being told? And would a scale bar help? So to give you a little background, this map was presented when there was construction on Route 7 in Pierce County, rural Pierce County, and this was the map that was presented online to go with the article about the construction. This is an image that was presented as a map of the day. It's actually my personal favorite, my number one personal favorite map of the day. It was submitted by Janelle Kay and her daughter, who was at the time 6 years old. This was back in April of 2017. And it says, Janelle wrote, "My 6-year-old daughter has been trying to figure out what she's doing, and this is her interpretation." And if you can't read it, it says maps have squiggly lines and roads. And there's a couple images. And then in terms of a cartographic critique, Janelle adds, "I would have added a reference map and perhaps a legend," with a smiley face. Of course, she's joking. This is pretty darn good for a 6-year-old to present. And I just think this is the most beautiful thing. My second favorite was completed by Masha P., who was 12 years old, while on a flight from SeaTac to Frankfurt that was also connecting to Moscow. And this was June 27th, 2018. This was created by Masha. She drew the lines and she put in some labels. She has a 10-hour flight with a little play on words, which is pretty interesting given that her first language is Russian. Her second language that she learned starting when she was 11, second language being English. She has supposedly Greenland that is all white. So she's making observations about the map that was presented to her. This was done on the back seat of her, of the person in front of her, from what I understand, and then she added these on her phone. She has a 5-hour stop, 3-hour flight from Frankfurt to Moscow, and she marks home. No, I just thought I'd share those with you. This is a placeholder for Lab 1 bonus maps, placeholder for Lab 2 bonus maps. I hope that a lot of you submit Lab 2 bonus map. There were a lot of Lab 1 bonus maps. By the end of this lecture, you should be able to describe the difference between geographic and projected coordinate systems. And the learning plan was designed to help you with that, as well as the readings, and of course this lecture. In class, if I were to ask, hopefully you could describe it in just a few words. It should be pretty easy. And I've just listed the learning plan that you completed. Hopefully you completed in preparation for Lab 3. And that's what this was for, is designed to prepare you for Lab 3. Week 5 learning plan is, Week 6 learning plan, because this is it is Week 5. I apologize. Learning plan. So this week, preparation for Lab 4 has been assigned. There's only 2 courses in it. And that's because Lab 3 is a little bit longer than other labs, a little bit more detailed. You're getting into the heart of GIS. You'll be completing Introduction to Spatial Data and Integrating Data in ArcGIS Pro. These are two very good classes. And then for next week, week 6 learning plan prep for lab 5 has also been assigned. Check your email and be sure to accept it. This one includes editing basics in Arc Pro and ArcGIS Pro editing essentials. These will help you prepare for lab 5. In preparation for lab 3, these videos that I've selected do a great job of discussing and explaining the differences in coordinate systems. And it's far better than reading dozens or even hundreds of pages of content. If you'd like, you can read hundreds or thousands of pages about coordinate systems, but for our purposes, these videos are ideal for understanding the importance of lining up our data and using the correct coordinate system for our projects in Arc Pro, and eventually your projects when you work on maps on your own. So these were the required videos in the module. This is a YouTube. This gentleman right here, it was cutting the globe open. This is a video that maps that prove you don't really know Earth. So that's an interesting video. And then there's a video that references Lab 2 that talks about campaign maps and money that I thought you may find interesting now that we're talking about projections and coordinate systems. There really aren't projections and coordinate systems in this map, but they are distorting maps based on criteria that they explain in the video. I'll let you watch it to see it. This image here is a map that was displayed on the West Wing. That was also a video to help you understand coordinate systems and projections. This was 2020 in September. There were some heavy clouds hovering over Tacoma and most of the Puget Sound. And then there's this mynorthwest.com story about the air quality. And they talked about how 11 counties received F grades for air quality, but they didn't include a map. And I found that very interesting because all of you now could spend 15 minutes or less, given the right information. Everything you've done in Lab 2 or leading up to Lab 2, you could have prepared a decent map for them, and it would have been better than nothing. So what I'm saying is your skills are going to be highly valued, especially once you complete this course and perhaps courses beyond. So if you'd like, take a look, click on this link, and just think about what kind of map you may have made. Just detailing the 11 counties. What would you include it? What would you have left out? And in thinking about this, I thought about where's the beef? So where's the map? The beef being the most important part of the story, the 11 counties that received that F grade. How would you symbolize that? And what type of background might you use or legend? And then I got thinking, okay, I should really show these commercials that I'm talking about with Where's the Beef. So these are about 15 seconds or less, each of them. I encourage you to click on them if you don't know what I'm talking about. They are pretty hilarious, and they are actual commercials that were on TV, and I think you'll get a kick out of them. Some questions for the day. How and why do we line up our data? What is a geographic coordinate system? What is a projection? What is a projected coordinate system? So why we line up our data, it's important for visually represent the data so it's pleasing to the map viewers. We need it so that all of our data being lined up, we can perform accurate analysis and to actually have the right area of our data. If we distort our data, the area is going to be highly distorted if we don't use the right coordinate system. So it's an important part of GIS, and it's one that you have to master in Lab 3 so that you can utilize it in the remaining labs this quarter. The geographic coordinate system is it's a method for describing the position of a geographic location on the Earth's surface using spherical measures of latitude and longitude. And so you're trying to locate a point on the map on the Earth using XY coordinates, or latitude and longitude. A projection is a mathematical transformation that converts those spherical units of a GCS, geographic coordinate system, to units of latitude and longitude of a planar X and Y coordinate system. So planar being a flat coordinate system. So we're going from a globe, or the sphere of the Earth, to a flat map. So you can think of projected maps as flat maps. And given that, what is a projected coordinate system? A projected coordinate system is defined on a flat two-dimensional surface. Unlike a geographical coordinate system, a projected coordinate system has constant lengths, angles, and areas across the two dimensions. A projected coordinate system is always based on a geographic coordinate system that is based on a specific sphere or spheroid model. So these projected coordinate systems are based on the geographic coordinate system. I've got some more vocabulary for you. There's some links that you can click on to find these definitions, and I will give them to you as well. A geoid is the shape of the Earth defined by mean sea level affected by topographic and gravitational factors. Graticule is the marks of latitude and longitude forming a grid on the globe. For example, the geographic coordinate system, latitude and longitude, X and Y. Geodesy is the science of accurately measuring and understanding three fundamental properties of the Earth: its geometric shape, its orientation in space, and its gravity field, as well as changes of these properties with time. So an ellipsoid or spheroid, a sphere is flattened at the poles, a spheroidal volume with unequal axes used to approximate the shape of the Earth in map projections. A datum it defines the position of the spheroid relative to the center of the Earth. A combination of an Earth ellipsoid and a reference point to reduce mapping discrepancies for a particular region. A geodetic datum is an abstract coordinate system with a reference surface, such as sea level, that serves to provide known locations to begin surveys and create maps. In this way, datums act similar to starting points when you give someone directions. For example, when you want to tell someone how to get to your house, you give them a starting point that they know, like a crossroads or a building address. Geodesists and surveyors use datums to create starting or reference points for floodplain maps, property boundaries, construction surveys, levee design, or other work requiring accurate coordinates that are consistent with one another. There are two main datums in the United States. Horizontal datums measure positions, latitude and longitude, on the surface of the Earth, while vertical datums are used to measure land elevation and water depths. And then a projection is a mathematical transformation that converts spherical units of latitude and longitude to planar XY coordinate systems or a flat surface. And I provided those for you here. The previous two slides combined into one so that you have these definitions of the key vocabulary terms. And I know it's hard to read, which is why you can print this out and you have it in front of you. So here's an example of distortion. 50 degrees east of the international date line, so going from 0, 50 degrees east. Let's look at the length differences between that measurement at the equator and that measurement at 40 degrees north. So if we go 40 degrees north and create that same horizontal line, which of these two lines is longer? The distance here at the equator or the distance at 40 degrees north? And in fact, it's the longer line, of course, is the equator because it's bigger round in the middle. So it's going to be a different distance. So this is the same angular unit. It's still 50 degrees at 40 degrees latitude as it is at 0 latitude. But at 40 degrees north, the distance is shorter. So you notice that this gold line is the distance the same as the purple line, but it goes all the way over to here. So this distance is shorter as you get to the poles. So if you picture this, when you project it and we flatten out these lines of longitude, there's going to be distortion in this measurement. It's going to get wider as we flatten out the globe. And here's virtually the same image. Usually we talk about latitude and longitude when really when you say latitude and lat and long, your first measurement is actually coming from the longitude. So I just wanted to throw this little brain teaser in there for you. 50 degrees east, 40 degrees north is technically 50 degrees longitude and 40 degrees latitude. So it's 50, 40. The longitude value is usually first and then the latitude. This corresponds to the XY pairs in a Cartesian coordinate system. On the globe, the x-axis would be the equator. However, the numerical values come from the lines of longitude. The y-axis is the prime meridian. However, the numerical values actually come from the lines of latitude. Negative x values represent locations in the western hemisphere, while negative y values indicate locations in the southern hemisphere. Locational information does not have to be latitude and longitude. It could be a street address or anything else that can be geocoded, mapped, or based on some specific location. The diagram on the left shows the differences in a geographic and projected, how the measurement would be different. So on a geographic, the line is much longer because of the arc than what it would be flattened out. So the projected plane is quite longer than what it would appear on the geographic plane. So notice how this stretches out, whereas the distance is actually from this here to here, or that's what it would seem to be. So there are two types of coordinate systems, geographic and projected. Projected are flat, whereas geographic are spherical. When we convert from a real life geographic to projected, the values become inaccurate, as noted in the desktop image, Esri desktop images presented here. Note the Earth's surface versus the flat surface. The second image also shows distortion. And in this example, we have a light bulb and a globe, and then a cylindrical projection. And while these two lines down here are the same distance apart, if they were measured properly, they actually appear longer. And the same with the lines of longitude, the areas are stretched. So you can visualize the light going through a clear globe onto a piece of paper. And these distortions are what causes us a little bit of hassle in Arc Pro, and we have to utilize the correct projection so that we minimize that distortion. The types of projections, you could have a conic, which is tangent, conic secant, cylindrical, and this would be a normal cylindrical, transverse cylindrical, and oblique cylindrical. Planar, such as here, very flat against the globe, and polar, which is this image over here. There's distortion in all projections. Some are drastic and some are slight. Projections are chosen to minimize the distortions for the particular aspects of the data. In ArcMap, we could get rid of on-the-fly projections. And this is just a silly image that I created with a projection on a fly. And here's the link to the fly. And this is an Esri image that I grabbed. But we cannot rely on the fly projections. So what that means is our data, our actual data, needs to be properly projected to the same coordinate system. One of the most important points of getting the projection to your ideal projection is using the right tool for the job. If you use the incorrect tool for the job, you're going to mess up the data, and you probably will have to restart with fresh data. So if you're using a raster, you would always project raster. That's the easy one. With vector data, there's a couple choices, and we're going to talk about that in detail towards the end of this lecture. For vector data, you'll use define projection in some cases and then project, or you will just use the project tool. And again, there's an important reasoning behind this in using the proper tools. So you know, define projection only changes the label of the coordinate system. It kind of sets the starting point for the project tool. It does not change the coordinates. It does not change a new data set. And it's only to be used when there is no coordinate system information. So that would mean that coordinate system is blank, it states undefined, or it states unknown. That is the only time you use define projection. The project tool does create a new set of data in a different coordinate system and most likely projection. It changes the definition of the data, it creates a new data set, and it's only used when the data already has coordinate system or projection spatial information. So those are the distinct characteristics for vector data. With raster data, you always use the project raster tool. So what is this difference in coordinate systems? Well, here are 3 different coordinate systems. There's a geographic coordinate system, latitude and longitude, and this one is outlined in green. So you can see the faint green lines. There's also a Mercator projection in red. And then there's a blue Lambert conformal conic projection. And you can see by looking at this map, if all of the data points were lined up, for example, in the center, you can notice that if your data was in Lambert conformal conic, and then some other data was in green, unprojected latitude and longitude, it doesn't line up. And Tacoma would not be over Tacoma if you had 2 layers that included Tacoma parts, for example. Tacoma parks, maybe in green, would not overlay with the Tacoma boundaries. And it's a phenomena that happens in GIS when you have data that's in different coordinate systems. And that's why we have to line up our data. And this is all spelled out here by Peter H. Dana, by the way. Here's a coordinate system that we use for Pierce County, Washington. It's called UTM Zone 10N. So this is the Universal Transverse Mercator System. We are in grid 10 because 10 intersects Washington. And then we choose N because we are north of the equator. You won't always use UTM Zone 10N for Pierce County, but if you want to use UTM, Universal Transverse Mercator, you will always use Zone 10N for Pierce County, and that's for the accuracy. If you were to choose, 38N, that projection is created for somewhere over here in Eastern Europe. So or Russia, whatever it happens to be. That coordinate system is best for that area, whereas the one that's best for Washington is 10N. This is another image. I just found this one of a geographic versus a projected coordinate system. The geographic, of course, is on the left, and the same dot is placed on the maps. The one on the right is in meters because it's a projected coordinate system, so it's measured with meters. In this case, it could be miles, it could be feet, it could be other planar measurements, versus in degrees on a global or spheroid geographic coordinate system. Given these 2 images, you should be able to remember which is which. If this detailed information wasn't here on the bottom, you should be able to immediately recognize that this is a geographic coordinate system and this is a projected coordinate system. And speaking of distortion, you can see how big the South Pole looks down here with the land masses just stretched considerably. So how do we do this? What do we do in GIS 311, 312, and 414 and beyond? Typo. There's a simple rule. The first step with all data is to check the coordinate system and projection of the data. It may have both. It may only have one. If it only has one, it'll be a geographic coordinate system. From there, you choose an appropriate coordinate system and projection for your mapping or GIS needs. And then the rule to get the layer and the data into the correct spatial reference is if the data does not have any spatial reference of any kind, or if it's unknown, always in GIS 311, 312, and 414, You must always use the define projection tool first, and you will define the projection to a geographic coordinate system. Choose North America, choose USA and territories, and then 1983. Then you'll use the project tool for the desired projected coordinate system. The reason we choose this defined projection is there was a time when data didn't come with any coordinate system. It was a known fact at that time that the coordinate system was geographic North America, USA and territories, NAD 1983, and to save space in the file, that bit of information was stripped from the file. So it actually made the file a little bit smaller. Therefore, we all know it's just for this class. You can't use this for all data, but in my classes, I will only give you data that we know should be defined to geographic, North America, USA and territories, NAD 1983. If you have data from other sources, you'll need to look at the metadata or the information that comes with the data that tells you what the coordinate system should be. And you definitely need to find that, particularly if you're working on your own project and there is no spatial reference in the data. You may want to ditch your data and find something that does have a spatial reference, or find data that comes with the metadata to tell you how to define your data. And then in the chance that it does have spatial data, if the data has any spatial reference, doesn't matter what it is, if there's just something in there, a geographic and projected or just geographic coordinate system, all you need to do is use the project tool. And you remember a few slides ago I talked about using the proper tool. This is where you decide which tool to use, and in the case of defined projection, you just learn what you would define the projection as. And again, for clarity, geographic, North America, USA and territories, NAD 1983. And this is a little bit foreign to you right now. You probably haven't even done it yet, but in the lab and in the demos first, you'll see me perform these operations and it'll make a lot more sense. Lastly, you should keep track of your coordinate systems for every single layer in your map. And for that, you'll create a little grid, probably in Excel, to keep track of your data and the coordinate systems. And we'll talk more about that as well. I've created a simple little cheat sheet. It's the same as the previous slide, but it's written more like a flow chart or something you could follow. Does the data have any spatial reference of any kind? Well, let's make that italics. Yes, there is some spatial reference. Then you simply use the project tool for the desired coordinate system. And that could be geographic or projected. Either way, you can use the project tool in this instance for geographic or projected. 99 times out of 100, you'll use a projected. But they're both called coordinate systems, so that's why I just specified coordinate system. No, spatial reference is either undefined or unknown. So that is, does the data have any spatial reference of any kind? The answer being no, then you must always use the define projection tool. And again, you should remember this from the previous slide. Define projection to geographic coordinate system, North America, USA and territories, NAD 1983, and then use the project tool for the desired coordinate system. And this is the process you either completed or will complete with places WA, that's the data in Lab 3. And again, you must also keep track of your coordinate systems for all of your data within your map so that you can get them all to line up. Moving along, there will be skills demos in class that complement this lecture. So you'll see this being done in class via Zoom or in person. Depends on your class, so make sure you know if there's ever a Zoom or if it's in person. This is a friendly reminder to please complete the midterm course instructor evaluation. That helps me with my progress as a professor. Positive news is always great. It helps me advance in my career. And it also helps me help you in the middle of the course, because halfway during the course you have a chance to give me feedback to help me improve the course for you. And hopefully by now you realize that I'm always open to hearing your ideas. You can talk to me in class, after class, send me an email, remind me that I forgot something, etc. I'm happy to hear from you, and I never take offense. As long as students act professional, I'm happy to talk with you about any concerns you may have. And I will treat you with the same level of respect all the time. Absolutely. And we have reached the end of Day 5 lecture for GIS 311. Please be sure to check Canvas for everything that is due. This preparatory lecture for week 5 is just the beginning. There are other things that you should look at. There's some videos, there's some links. I gave you plenty of links in this lecture presentation. Some links to watch a couple great videos to help you comprehend this very difficult concept. This is a work in progress. You won't figure it out all this week or next week. Just by doing GIS, though, over the course of the next 4 or 5 weeks, and if you take another class, then it will start to make sense. I will note that coordinate systems and projections were my most difficult concept to comprehend. I always struggled with it, and that's why I've taken great care to prepare this lecture that in a way that I think is more easily understood than just using the textbook definitions. But please come to class with questions. I'm happy to answer any and all questions, and if I don't know the answer, which is sometimes the case, we'll look it up and figure it out together. Well, thank you very much. I look forward to seeing all of you in class and helping you get a head start on Lab 3 and hopefully completing it by the end of class day. Thank you very much. I'll see you in class.